is at about this point in the semester when we're going to start to examine lots of different properties that you can determine from a pretty simple thought process. But if you, again, try to approach this from a standpoint of rules, it's going to become absolutely overwhelming. There's no way in the world that you can remember all of these things, especially not in college when you're learning them so much faster than you would maybe in high school. And so I'm going to go through this packet with you today, but I'm going to do it from a standpoint of showing you how we can figure out these answers by just taking a little bit of time and trying to think about through what the questions would be, or what the meaning is, or what the model of logic in front of us is trying to communicate. And I'm going to show this to you for the reason being that when you are taking a test, or when you're in a future math class, or when you see something pop up in real life, I want to remind you that saying you don't have the answer or you don't know what to do is a really, it's an inopportune method for approaching problems. Instead, focus on something you do know for certain and then build up from there. So let's take a look at what I'm talking about for this one here. Today we're going to be talking about transformations of functions. And so let's take a moment and just break down what that word is talking about. First of all, we know what functions are. Functions are something that we know for certain. Functions are a miraculous process, we could say, a computer program, something happening behind the scenes, a general umbrella term for saying, I have a question and I'm going to use a function to get me an answer. And you can think of this in being a miraculous process. We're going to see that there are many different miraculous processes that we've looked at so far in math that can be called functions, but for right now, we can always just say functions are some sort of magical transition from a question X into an answer Y, where every time I ask a question X, I get one answer Y at most. Now, the transformations of these functions, what we're going to be doing is if we have some kind of relationship like this, we're about to be adjusting it. So we're about to be saying, if I ask a question X, what happens if instead of getting Y, I wanted to get 2 times Y, or maybe I wanted to get Y minus 2, or maybe I wanted to get Y divided by 2. What if I wanted to get these things instead? Y might be a really nice jump off point for me, but then there's some additional logic that I can always kind of use to transform my answer from my original setup to maybe something a little bit more specific. And maybe the best way to think about this is we're going to start to learn the art of tailoring functions. And tailoring functions, just like if you get a custom tailored suit or tailored shoes, these are going to be functions that fit a very specific purpose, that start from something generic and then become something very specific. So let's do that originally through an exploration. Let's sketch the graph of f of x equals absolute value of x. And by now we've played around with these graphs enough, you really want to be able to follow this in a quick manner without having to go back and like plot points each time. So when I am sketching the graph of absolute value of x, I can remember from my earlier play with that that's going to be a V-shaped graph. And it's a V-shaped graph because of a couple of different reasons. One, it's linear on the right-hand side, because I'm not doing anything from 3 other than getting me a value of 3, and then I can think of it as being symmetric across the y-axis because it's an even function. In other words, an even function because anytime I ask the negative question, I'm going to get the same answer as I would if I asked the positive question. So here we are. This is the graph of f of x equals absolute value of x. Now, how does it compare to the graph of absolute value of x equals 2? Well, we don't necessarily have to memorize what absolute value of x equals 2 in terms of a graph. We can use this other one as a reference. So maybe I'll call this one orange. But now I'm saying that I have an absolute value of x, and every time I get one of these answers, I'm about to transform it by growing it by 2. So do we kind of see that? Like the first thing is I ask a question, and then in order of operations, I would find the absolute value of x, and then after that, I would add 2 to it. So we could say each of these points are being grown by 2 in my new transformation. I'm transforming everything to be 2 bigger than it used to be. And if you do this across all of the different points in this graph, you can actually get something that looks, again, like a V-shaped graph. It's just 2 units higher at any given x value. And so this is a nice quick way for us to be able to say, I can graph g of x equals absolute value of x plus 2 without having to go through the idea of saying, well, what's the answer that I get when I'm at -3? How does that absolute value? Do I add 2 to it? Do I put that in a table? Do I plot coordinate points? No, I'm just shifting everything up 2 because that's what it means to take an original function of absolute value of x and to add 2 to it afterwards. Okay, so let's go ahead and I'm going to leave you with this one. Write a summary explaining why the graph shifts up in this way. That's for you to do. We'll pause the video right here. But I want to show you the power of taking time to what's called abstract out this thought. This exploration really gives us the opportunity to draw a lot of different graphs from a really quick starting point. So for example, f of x equals equals x squared plus 1, we could say that this is the starting place of maybe an x squared graph. That would be like this. That recalls something I'm familiar with. And then if I wanted to add 1 to it, then that would be just shifting all of this up 1, so that if any given time I grabbed an x value, my original x squared would have been here, and above it is 1 higher to get me my x squared plus 1. So there you go, a nice quick way for us to be able to sketch these out. Let's try to do this with x cubed minus 2. We might remember that this is a cubic graph that kind of looks like an S turned sideways, where we can remember that -1, if I cube it, would get me to -1, but +1 if I cubed it would get me to +1. So that's why we got our points here. This is what we would call maybe our parent function. We're starting from this, and we're about to get a child function from it. We're going to try to reference something back to this, and that's going to be x cubed minus 2. So now I'm about to take all of these points and shift them down 2. So I'm going to try to take this one, I'm going to shift it down 1, and I'm going to shift it down 2. So that's going to be my new point here. This one was at the origin. I'm going to shift it down 1, and I'm going to shift it down 2. That's going to go right here. This one is going to shift down 1 and then shift down 2. So it's going to go right here. And if you clean up all of that work and then draw it all in, what you're going to see is you've got that exact same S-shaped curve, but that S-shaped curve is going to be 2 units below the original one. So it's going to be just like this. And it kind of hugs in a little bit closer there. Make sure that you're nice and artsy about it, but that's exactly what we're looking at. And I'll make sure that this one maybe is blue to keep the motif going. Good, so we've shifted from the blue to the orange, and then we could erase our sketch lines if you wanted. So you could then go back and erase this and say what the actual graph of x cubed minus 2 is just this orange, and the actual graph of the x squared plus 1 is just that orange. Or maybe do it with dotted lines, or make yourself a little note that that's just a reference place. Okay, so maybe I'll start doing that in the next one. I'll start doing it where maybe I use dotted lines as my reference. So absolute value of x, remember again, is that V-shaped graph. So maybe I'll do a dotted graph because I'm not done drawing yet. I just want to get my thoughts on the paper. And then I'm about to shift it down by 3. So I can go ahead and put that in with this orange. I'm going to shift it down 3, and that's going to be my actual graph, is this one right here. Very nice. I like this idea of kind of having the dotted lines as my reference before I put in my final answer. Okay, what about this square root of x plus 4? Well, the square root of x plus 4 is just from the parent function of square root of x, that's what's happening first, and that would have been this graph. That's like a parabola turned sideways, but I'm about to add 4 to it, so we're going to grow it by moving the y value up by 4. That's going to put us right there. Very nice. Now keep in mind, the reason why we're growing by 4 can be thought of in 2 different ways. We can think of it as saying I've got an answer, my square root of x, and I'm adding 4 to it, so I'm about to grow it at the end. Or we may remember from an earlier lesson that one way we could also view this is by rewriting this into a different perspective, like we had with our circles. We could look at this as a transformation, like saying instead of g of x equals absolute value plus 2, we could look at this and say maybe instead of g of x, which is just a function, we could write down that what we're really doing with our answers is getting some kind of height, y, so we can make the logical jump to say our functions can be thought of as giving us different heights, and my heights are called y. And we could even look at this in terms of something like y minus 2 equals absolute value of x. And we start to notice this looks a little bit like that h minus or x minus h or y minus k structure that happened with our circles. And that when we were talking about that, what we were saying was that what's really happening, I'll erase this one for a moment, is that what we're doing is we're taking y and we're shifting down 2, but we're shifting not the graph, we're shifting the entire coordinate plane. So just as another way that we could look at this, we could have, instead of taking one of these functions and jumping it up, we could have looked at it as saying, well, really what we're doing is y minus 2, so all of the y values in my coordinate system are minus 2. And so what that means is that I'm actually taking my entire coordinate grid and I'm shifting it upwards. To show you that, let me jump back over here to Word. So what I'm saying is that if we decided to look at this through a different perspective, we could view this as y minus 2 equals absolute value of x. And whenever we have something that is being subtracted from our y, we could view this as changing the entire coordinate plane, because I'm literally taking all y values and I'm shifting them down. So we're going to first graph our v shape, and then just like I did in the lecture for circles, you can think of it as saying I'm then going to grab the entire coordinate system and I'm going to move everything down y by 2. There you have it. So that's another way that you can look at it. You can look at it as shifting the graph up by adding 2 to the function, or you can look at it as saying really what you have on the left-hand side is an equivalent expression of saying y minus 2, and whenever we are subtracting something from y, or subtracting something from a variable, that means that we're taking that entire coordinate system and just moving it down. Or what we're about to see is that we're about to be doing things where we have x minus 2, and that means we're going to take all the x values and move those sideways. So this is where we get into the tricky part, and this is what I was just talking about a moment ago. So here we have a situation where we have f of x equals the absolute value of x. So again, let's go ahead and plot that in. That's going to be something that looks just like this. But I'd like to use this as a reference for graphing absolute value of x plus 2. Now it's going to be almost, it feels like what we have to do is the same thing we did before, where I'm just going to take x and I'm going to add 2 to it. But keep in mind, that wasn't the story that we were just exploring. Remember, the story that we had above in our packet was that I was looking at taking a function, and then I was going to add 2 to it after I had gotten a height. But I wasn't doing anything with y on the right-hand side here. I wasn't doing anything with saying y plus 2 was the reason why I was adding 2 to it. In fact, what I had to do when we wanted to talk about those y values is we actually had to get something next to the y value. And we actually saw the opposite. When I'm subtracting 2 from y, the meaning behind that entire thing is you're grabbing the coordinate system and you're moving it down. Every y value now goes 2 less. So a y value of 2 is now a y value of 0, a y value of 0 is now a y value of negative 2. So when we look at variable plus or variable minus, we're moving the coordinate system. But when we're looking at function plus, what we're looking at is growing the values. They're two sides of the same coin. They get us the exact same picture, but it's up to you to kind of keep track of what's the storyline you would like to follow. Now in this one here, it becomes really, really helpful for us to view it in that idea of taking a variable and then adding or subtracting to it, meaning that I'm shifting the coordinate system. So let's take a look at what I mean by that one. If I wanted to really quickly just do a little bit of comparison, I could look at my original and say that originally, if I had an x value, I was finding an absolute value of x. So originally, maybe I found an x value of, I start with -1, absolute value of -1 would be 1. Absolute value of 0 would be 0, absolute value of 1 would be 1, no problem. Now I'm looking at this new table that I've transformed everything into, and I'm saying I have x, no problem, maybe x is -1, and I want to figure out the absolute value of x plus 2. So now I'm doing the absolute value of -1 plus 2, which is the absolute value of 1, which is 1. Okay, interesting. Oh, just 1. The next part is saying, if I put in, let's say, I put in 0, now I'm doing the absolute value of 0 plus 2, that would just be 2. And then 1 would be, I'm taking the absolute value of 1 plus 2, that would be 3. So what we've done is we've actually changed all of our f of x values to something different. So we've taken this, and let's plot that all in. I'll use a different color. We'll make this orange here. So this is going to be my little star here to show that this is what I'm about to plot as orange. Now -1 corresponds with, let's see, 1. That looks like it's the same. 0 corresponds with 2. 1 corresponds with 3. And if you actually work backwards, -2 would correspond with 0, -3 would correspond with 1. And so we've actually, by adding 2 inside of the argument, inside of that absolute value, we've actually taken the entire graph and shifted it 2 to the left. And this feels, again, very odd. Why is it that adding 2 causes everything to shift to the left? And it's because we need to look here and see that I have x plus 2, and so if I'm taking all x values and I'm adding 2 to it, that doesn't mean that I'm taking my function values and adding 2 to it. That means I'm taking my x values and I'm moving all of them over. So let's again jump over back into the Word document, and I'll use that as an example to show you. So what we're doing by adding 2 is we're starting off with this graph of absolute value of x. And we'll put it in right over here as well. But by growing everything by 2, we are taking all of these x values, like perhaps this value right here of 3, and I'm about to grow it by 2. So watch what happens when we do that. We've moved the graph to the left because we grabbed the coordinate system and grew it by 2. So this is what's happening when we're talking about adding numbers to variables or subtracting numbers from variables. We're literally moving the entire coordinate system that amount. But if we want to look at it in a different perspective, sometimes we can view it as shifting things, shifting the actual graph to the right or left. I prefer the idea of moving the entire coordinate system underneath the graph, but you choose what you like the best. They're the same idea, just different perspectives. Okay, so it's on you to write a summary explaining why the graph shifted left when I added 2 to it. But we can see that the idea here holds pretty steady, so we can really quickly abstract this to a shortcut if we'd like. So if I look here at this graph here, this looks very similar to f of x is equal to x squared. It just looks like instead what we've done is we've taken the x value and we've subtracted 3 from it. So in other words, we're taking this entire coordinate system and moving it to the left, which is going to result in us picking up our graph and moving it to the right. Here's what I mean by that. So let's start off with black as our little reference line here. It's we'll use blue as my reference as my parent function. So this is originally what x squared looks like, as a nice parabola. And you can label that as f of x if you'd like. And then if I wanted to, let's call it g of x. I have f labeled twice. We shouldn't have that. Let's make this one g. There we go, g of x. So that's my parent function. I'm going to make it into f of x, and I'm going to do that by grabbing the entire coordinate system and moving it 3 to the left. I'm subtracting 3 from all of my x values. So that's grabbing these x values and subtracting 3 from them. What the result of that is going to be is us grabbing this picture and shifting it 3 to the right. So now, whereas we originally would have had a 0, 0 value here, now this is going to be a 3, 0 value. So we've moved everything to the right by 3. Okay, take a moment and give yourself plenty of time to really marinate on this and to see why all of these transformations are working the way they are. We're taking all of the coordinate system and moving it 3 to the left. The result is that the picture looks like it's 3 to the right. Okay, let's do this next one. And we'll start to really get comfortable with this shortcut idea. So the shortcut here, again, is I'm going to be adding 4 to x, which means I'm grabbing all of these x values, and I'm pulling the rug out from underneath my graph by moving it 4 to the right. Okay, so I would have originally had this f of x value looking like an x cubed graph, it looks like. But then by changing the coordinate system, by pulling that rug out from underneath it, I'm going to be adding 4 to it, which is going to make it look like it fell 4 behind. Just like that. And we could label this one F in our notes so we keep it nice and organized. So that was F, the other one was G, some kind of parent graph that we are referencing. So we'll say G, which is here, g of x was our reference parent function, x cubed. Okay, nice. Let's do the other ones a little bit faster. So this one, next I've got f of x equals absolute value of x. So I'm thinking we could start off with the parent function of just, again, the absolute value of x. We're gonna add 2 to the x, which means we're gonna take all these x values and shift them over from the whole coordinate system. We're picking that up and moving that. It's gonna make this graph look like it's drifting behind. And so that's gonna put it over here, where it's essentially like it's shifted 2 backwards. Okay, and then this square root of x graph is going to have started off where I had my square root x. But again, I'm gonna grab all those x values, and here it looks like I'm going to subtract them by 3. I'm gonna shift that entire picture, the entire coordinate system over by 3. It's gonna make my picture look like it's shifting to the right. Very nice. Okay, good. Let's keep going with our exploration. Now we might be curious about what happens if I take some kind of graph, let's say f of x equals 1 over x plus 1. Now this is a scary looking graph. Let's take a moment, maybe do some scratch work with this. I have f of x equals 1 over x plus 1. Let's pull out just some things that we observe from this to help give us some standpoints. First, you should by now really be sensitive to the fact that if I have a variable in the denominator, there's a possibility that I will have a divide by 0 error. And that's gonna occur here when x is -1. So at x is -1, I'm gonna have a problem. So I'm not gonna have a value that's going to appear above x equals -1. And then I could ask myself and say, okay, well, this 1 over x plus 1, what actually is happening? Well, I guess that kind of looks like the parent function of g of, I don't want to use g of x. Let's use, I have f, I have g, I have h, maybe we'll call it k. Okay, so we're just creating our own models here. So let's say this looks kind of like that k of x graph, that would be 1 over x. But again, it looks like I'm taking x and I'm adding 1 to it. So that means that I'm taking the whole coordinate system, I'm moving it 1 to the right. That's making this whole thing drift behind. Oh, okay, so that's orange one should look just like our 1 over x graph, but I've got it shifted a little bit to the left. Good, very nice. So this is gonna be f, we'll label it as f. Now I'd like to try to graph this g of x, which is the negative of, it looks like all of that. So let's take a moment and think about how I can connect that. There's a couple of different ways we could do it. I'm gonna write it with symbols, but I'm gonna tell it to you as a story. You could look at this and say g of x is actually equal to the opposite of f of x. Now that's a lot, so let's take a moment and break that one down. Here's f of x. It's just the positive version of 1 over x plus 1. Here is g of x. It's the negative version of 1 over x plus 1. So there's nothing wrong with me saying g of x is just the opposite of f of x. So let's now figure out exactly what I'm oppositing. If I have all of my heights that were popping out and now I'm about to make them negative, then I guess what we're doing in this g of x, which I'll graph with a negative, is I'm taking all the points that would have been here and I'm flipping them to their negative equivalent. So I'm taking all these values and I'm just flipping them to their negative equivalent. I'm taking all these values and I'm just flipping them to their negative equivalent. Wherever that goes, that'd be what, 4 or 5-ish? It's like all the way down here. That's like a huge flip. All right. And then I'm doing the same thing with this one over here where I'm flipping it. And so that's gonna get me like here. And then this is all gonna go up. And then this one's going to be down like this, connecting all of my dots. And maybe I'll clean up my work in a second. Okay. So here we go, that's the thought process behind what we just did here, is we had a graph, f, and the negative of that is just where I flip it over that x-axis. I make all of my heights negative instead of having them as positives. I'm trying to clean up as I talk here. Okay, so there we go, that'd be, the black one is now g of x. That works out just fine. Okay, so that works out pretty good. What about this one right here? This one here looks really close to f of x, but it's like my x values are all negative. Do we see that? The 1 is still positive here. I still have a positive 1, it's right here, but my x values are negative. Maybe that feels a little bit weird. Let's try drawing a new graph down here. And I'll tell you what I'm seeing. I'm seeing that h of x could be rewritten as being 1 over negative x plus 1. And then that looks pretty close to my f of x starting point, where my f of x value is 1 over positive x plus 1. So let's think about what we're doing here. Let's take our orange graph, we'll copy it down over here. This is where I started, was this parent function. And now I'm going to be making all of my x values negative. Okay, so let's take a look at what that would actually do. We'll do maybe blue here. So that means I'm taking this x value and I'm making it negative. Okay, I'm taking this value right here and I'm making it negative. I'm taking this value right here, which is negative, and making it positive. And then let's see, what exactly is that going to look like? This one's flipping over to here and to here. So I think this is going to come out like this. And I think this one's going to come out like this. And I think if we erase all of our helping lines, we should get that it's just the exact same picture as if I folded my paper in half. Okay, that looks pretty good. I'll put back in that axis in just a second. So it's like we're doing a nice little, I don't know, art creativity here. So if I make my x values negative, I'm just taking all the x values and I'm flipping them. I'm kind of folding it like a book, and I'm getting this symmetry where, just like before I was taking all of my things and I was flipping them below the x-axis, now I'm taking all the values and I'm flipping them across the y-axis so that I go from negative sideways distances to positive sideways distances and vice versa. Okay, that one's a little bit more challenging. Again, take a moment if you need to write a summary in your notes and explain what's happening when we have either a negative that is happening to the function as a whole, or a negative that is happening just to the x value. Okay, write yourself a little note there. But let's see if we can capture those ideas in a shorter, more effective method. So here I'm looking at y equals negative cube root of x minus 2, of x minus 2. Okay, there's a lot that's kind of going on in there. I can piece this out. What are the things we have? It looks like I am starting with y equals cube root of x, and then I am adding 2, which means that I am going to be, or subtracting 2, excuse me. I'm subtracting 2 from, nope, we gotta follow order of operations. See, this is why we write it all out. I'm having this and then I make it negative. I make those answers negative. So then I do negative of that, which means that I am flipping over the x-axis. Let me take a moment and explain my thoughts on that one. So I'm about to do the negative. I got a height. My cube root of x gets me a graph. Those all have a bunch of heights, and if I make those negatives, then those are now negative heights. Okay, so I'm making it negative. That gets me down to y equals negative cube root of x. Good. And then I've got the minus 2. If we remember that the subtracting 2 is where I am shifting my picture down, or you can think of it as shifting your coordinate system up. Either way. So I'm gonna think of it in this case as shifting my graph, and the graph is literally your picture, and not the grid, it's the picture. Shifting the graph down 2. Okay, so that gets us y equals negative cube root of x, and then a minus 2 on the outside. Okay, let's try to do all of that all together. We're gonna have to write and erase and erase and write, but we're gonna get there. Okay, cube root of x. That's the graph that looks like this. I am then going to make it negative, so I'm gonna flip all of my heights over. So I'll do that in a new color. That's gonna make all of my negative heights into positive heights, all my positive heights into negative heights. So now I am like this. Okay, so then I can erase this. And then I am going to shift all of this down 2. So then I'm going to grab this entire thing and shift it down 2. Right there. And there you have it. That's the entire graph. Not too bad. Yeah, not bad at all. We captured each of the layers of transformation that we did to this thing. Nice. Okay, let's take a look at this one here. What does this one look like? I think it looks like it started off as a y equals cube root of x. That's the parent function it makes me think of in my head. what happened here? I could think of it as saying the first thing that happens to x is I make it negative, it looks like. Okay, so that would be, first thing I'm gonna do is make it negative. So I'm gonna write in here, I've got negative x. And what does that mean? That means I'm taking all of my positive sideways distances and I'm making them into negative sideways distances and vice versa. So, okay, so this is going to be a flip over the y-axis. Okay, that's going to get me y equals cube root of negative x. And then from there, I think we are adding 1 to x. That's a little bit weird to see. Here's what I'm thinking. We could rewrite this one as being cube root of negative x plus 1. Oh, I like that a lot because now it's almost like I've got a story of what I'm doing to x. I have x, I'm making it negative, then I'm adding 1 to it. Okay, so that helps me see that maybe we could look at this as saying I am adding 1 to x, which means that I'm moving my entire coordinate system to the right one, which is going to make it look like it's going to the left 2 or left 1. So I'm going to say, okay, so that means shifting the graph left 1. And I'll write all my thoughts out. So I get y equals cube root of negative x plus 1. Okay, that I like. Now let's play around. So we've got the cube root of x graph. The cube root of x graph, oh, again, is just that S-shaped graph, like this. I am going to first be flipping it over the y-axis, so that's going to be like flipping it this way and flipping it this way. So we'll use a new color. I'll go to orange again and say if I flip it that way, I think we get to something like this. Which actually, interestingly enough, was the same picture we got to when we flipped it over the x-axis. So in this situation, when I flipped it one way or I flipped it the other way, it actually didn't matter. That's interesting to think about. We'll come back to why that is. And then I'm trying to add 1 to it, which shifts the graph left 1. Okay, so then I'm going to change this to blue, and I'm going to grab all of these things and I'm going to shift them left 1. And so my graph, I believe, should look something like this. Right? That's jumping over 1, etc., etc. Okay, there you have it. That's going to be how we graph these complicated, nested kind of relationships that are occurring in here by really breaking down and taking time to put our thoughts over here on the left. All right, so far, what have we played with? We played with subtracting and adding on the outside of a function. We've tried adding and subtracting in the argument of a function on the inside of a function. Let's now play with the multiplication and division that we could do and see what the effect of that would be. So everything else seemed to be shifting things up and down and sideways. What happens if I multiply instead? So now let's play around with, I would like to, oh, I think this is a typo. Let's make this f of x equals square root of x. Change your notes to that. F of x equals square root of x. There we are. So use the graph of f of x equals square root of x to sketch this one here. It looks like we're going to be multiplying by 2 on the outside, and here we're going to be multiplying by 1/2 on the outside. So maybe I'll make this a different color. We'll make one of these. We'll start with blue, then we'll go on, the next one will be orange, and then maybe we'll do green, I think. So let's make this one orange for our picture, and we'll do this one for green for our picture. Okay, so the first thing for blue, the square root of x graph. Square root of x graph, again, is going to be just like this, going on up. When you have these coordinates, these sideways values, we do want to be pretty careful to say that we land exactly where at least a few of our nice points are, like 1, 1. Square root of 1 gets me 1, square root of 4 gets me 2. So we want to make sure that if there are coordinates, we're not just sketching this loosely. But now I'm saying, okay, I'd like to grow all of them by 2. So I've got my heights. I'm about to take my heights and multiply those by 2. So let's get out the orange. Taking these heights and multiplying by 2. So now if I was at a height of 0, I am still at a height of 0 because twice the height of 0 is still 0. Okay. What about here? I was at a height of 1, about to do twice that. That puts me up to 2. Here I was at a height of 2, I'm about to do twice of that. That puts me up to 4. So it looks like I haven't shifted anything. Instead, I'm just kind of growing faster. Okay, that's kind of interesting. So that's the effect of multiplying by a number, is my heights are going up at a faster rate. I think that makes sense. What about green? What happens if I multiply by a number like that is smaller than 1? What's going to be the effect of that? Well, I was at a height of 1. Well, we'll say first I'm still starting at 0, because half of 0 would still be 0. Half of 1 would be 1/2. Half of 2 would be 1, and here we have it. The same general shape, but the shape is just growing slower. Okay, so that's not too difficult. So when we're talking about sketching these graphs, if we're multiplying on the outside of a function, then we can think of that as having the exact same growth behavior. It's just maybe changing at a different rate. Maybe it has the same general shape, it's just growing faster or slower. I like that. So if you want to add yourself a little note here, this would be a good thing to kind of write in your own words so that future you remembers exactly what's happening. But I'm going to bounce down to this part here. So now let's use the graph of f of x equals square root of x again to sketch what happens if I multiply by 4 before taking the square root, or if I multiply by 1/4 before taking the square root. Okay, so let's see what parallels we get here. I'm going to first start with blue again. So this is going to be, again, the parent function, that starting place, the square root of x graph. So it's going to be just like this. Make sure we go through our nice pretty points. Good. Here and here. Okay, and now I would like to multiply by 4, my x value is by 4, before I take the square root. Okay, let's see what happens with that one. I'll start off with maybe orange again. Let's do orange. Here we go. This one will be orange. All right, so 0 would be my first x value. I'm about to multiply that by 4. That gets me 0. Square root of 0 would still be 0. Okay, start there. What about number 1? So I'm going to take number 1, I'm going to multiply it by 4. This is going to get me 4. I'm going to do square root of 4. It gets me 2. So this one should take me up to 2. Okay, what about the next one? The next one is going to be, maybe I'm looking over here at 4. 4 times 4 would be 16. Square root of 16 would be 4. So now at 4, I go up to 4. Okay, so again, it almost looks like you have the exact same behavior. In fact, do we notice that it's actually the exact same orange graph as I had up here? Why do we think that is? Why was multiplying by 4 on the inside the same thing as multiplying by 2 on the outside? Well, we can use our symbols, our algebraic manipulations here to be able to see exactly why that is. Let's start with this one. Square root of 4x can be thought of as square root of 2 times 2 times x. And if I have a 2 squared like I do right here, that can be brought out as saying I have 2 times the square root of x. Oh, this is actually the exact same thing as up here. So even though in this one, the behavior, the storyline, said that I would like to look at x values that are growing faster and faster and kind of crunch that in, the result is that it almost made it look like the y values are getting crunched in, or are growing faster. Okay, so there's kind of different perspectives depending on how you want to adjust these equations. And similarly, you could see that this one here is 1/4 of x. Well, if I try to graph that, then here's the storyline. I'm going to take an x value, like maybe an x value of 0. I'm going to do 0 times 1/4 gets me 0, and then I'm going to do square root of 0 gets me 0. Okay, so after all of that process, I get an x value of 0 gets me a height of 0. What about 1? I have a x value of 1 times 1/4, and square root of 1/4 would be 1/2, so that would go up 1/2. And then I could say, okay, what happens for 4? If I put in 4 and I do 1/4 of 4, that's 1. Square root of 1 would be 1. So, look at that. It's the exact same picture again. Because, again, we could look at this as saying square root of 1/4 x is equal to square root of 1/2 times 1/2 times x is equal to 1/2 times the square root of x. Okay, interesting. So when you go through the story, as opposed to playing with the rules, sometimes we find these extra little added benefits. But what we're realizing is happening when we are multiplying by the inside of an argument is that the inside of an argument, you can write this down here, the inside of an argument, so if I have something like, oh, I don't know, let's do, what would be a good example of that? So if I'm multiplying by the inside of the argument, we'll have to kind of write it with a function notation. How do I write that? Okay, so we'll do it like this. I had f of x, and if I wanted to, instead of x, I wanted to put in something like 4 of x. Do we notice that that's what we did up here, is that I had f of x and it was square root of x, but now instead of x, I want to be putting in 4x. So it's really like I'm doing 4 times the argument on the inside. Okay, so what does this mean? This means that if I thought x was going to be 1, it actually goes to 4. So I'm actually running through my x values at a faster rate. If that's the case, then 1 is pulling the answer from 4 in to be 1. 4 is pulling the answer from 16 all the way in to be 4s. So we're kind of crunching everything in sideways. Okay, so this means that essentially what we're doing is we're taking some kind of graph. Let's do, I don't know, a nice little squiggle thing like this. If this was f, then what we're doing is we're grabbing those distances, those distant values, and we're pulling them in this way. So, and the reason being is, again, now the function's going to think that 1 actually means 4. So it's going to grab the value that was at 4 and pull it into where 1 is. Okay, so it's going to take this picture and squish it so that now what we have looks more like this. So we're taking everything and we're compressing it in because it's making the function think like we are at bigger values than we are actually at from our starting point. Versus if I have 4 times f of x, then what that means I'm doing is I'm taking some kind of picture like this, and I'm growing all of this to be 4 times as high. So that actually now it's going to be thinking I'm taking those answers and I'm making them 4 times as high. So I'm taking all of these values and expanding them out that way. Kind of interesting. So I want you to take a moment and go back through in these 2 pictures and think about why is it that in the square root specifically, whether I was taking the picture and squishing it in this way, or if I was taking the picture and stretching it out this way, what we were really having was the exact same result. And that's going to help you to kind of give a couple of different perspectives when you're playing around with your problems, where you're like, maybe I don't remember what this rule is, but maybe I can make everything look a little different, and I can use another rule that I remember. Okay? All right, let's take a look here now at objective 6. So this is combining all of them, and I'm going to just leave this for you. We're not going to do this all together. I'll maybe talk through a few of these as we're looking through them, but I want you to take a moment and write some shortcuts here. So what are we actually saying? The graph of y equals f of x plus c is obtained by, okay, let's break this all down. What's it actually saying? It's saying that I have some heights, or some function values, I guess we should say, some kind of would-be heights that I'm then going to add a positive number to it. So it's almost like I would have had a height of 2, maybe that I add something to it so it becomes a height of 5. What's going to happen with that in our picture? And you can sketch yourself out a little bit of a demonstration here, and then try to frame it into words for your own reference later. Give yourself a little bit of a curve, any kind of little squiggle, and then say what's going to happen if you try to grow this thing by adding c. And you might say, okay, well, if I had a height and I'm about to have a higher height, then I guess it's going to take this entire thing and shift it higher. Okay, and then give yourself some words here. How did you actually do that? What's the reasoning for it? What happens if instead of adding a number to this, you're subtracting a positive number from this? What happens if instead you are adding c to x? Keep in mind, here we're actually adding c directly to a variable. So if we're adding something to a variable, that's like shifting the coordinate plane in a certain direction that makes our graph appear like it's shifting in the opposite direction. Okay, so play around with that one, grab it from earlier in the task. What happens if you make all of the heights negative? What happens if you make all of the questions negative before asking them? What happens if you multiply by a number, right, that is positive? Remember, that's probably going to make the things grow at a faster rate. Like if now I have heights, but I have twice those heights, then that means I've probably got bigger heights. What happens if a is a positive real number and it's being multiplied on the inside of the argument? And actually, now that I'm looking at it, these are each going to have 2 different parts. For example, you're going to have one thing that says, well, if a is bigger than 1, then that would be, and did we have that in the instructions earlier? Let's see. Nope. So we're gonna have to actually have 2 different points. If a is bigger than 1, then that means I'm multiplying by something that should make my answer bigger. But if a was less than 1, then I'm actually looking at like something like a half or a quarter or maybe 0.8 or 80%. Like we're looking at those smaller amounts of height. So if I multiply by a number that's bigger than 1, you're probably gonna stretch it out. But if I multiply by something that is smaller than 1, I'm probably gonna bring it in. And if I multiply by a to my x values, that's going to make it look like I'm running through things faster and faster, which is going to pull things in tighter and tighter. Versus if I multiply by a and a is a small number, it's going to make it stretch out and become slower and slower. Take time, go back through that. If you have questions on it, flag me over, but this is going to be a nice cheat sheet for you to be able to reference, and so you really want to take time to develop this through. Okay, so let's now take a moment and use the transformations to sketch something like this. We're going to try to run through this again, everything together, using our rules from above. Use the transformations to sketch all this. Start with a parent function. The parent function here that reminds me of the structure looks something like y equals x squared. And we're going to ask ourselves, what happens to x squared to get it to all of this? The first thing that it looks like happens to x squared is I add 3 to it before I even square anything. Okay, so we're going to start with x squared. That's our nice parabola. Make it go through, we'll make that cleaner. We can have it go through a couple nice points like 0, 0, and 1, 1, and 2, 4. There we go. That looks better. Okay. We're about to take it from here. We're about to add 3 to x. So remember, that's going to take the entire coordinate system, shift it 3 to the right, which is going to pull the graph to looking like it's 3 to the left. Okay, so it's going to take our picture so that it looks like it's 3 to the left. And again, reference your cheat sheets up there for helping with the story. Okay, then I'm about to multiply by -2. So there's 2 things happening there. One, I'm about to take all the heights and make them negative. The second thing is I'm about to take all those heights and make them bigger. So I'm multiplying each height by 2 and I'm making it negative. Okay, so let's try that out. Height of 0 will still be a 0. A height of 1 is now going to be a -1 made into a -2. Oh, and sure enough, we're remembering our rule here that if I multiply by a number, I'm really kind of stretching those heights to make them bigger and bigger this way, like pulling this picture with like it's Play-Doh. Okay, so now I've got an even skinnier parabola that's going to be occurring as a result of all that. Very nice. And if I go back to my original problem, I think from here I'm going to subtract 1 from it. And so subtracting 1 from all of these heights, it's going to shift everything down. Okay, so it's going to take us to here, and then take us to here, I think, and here, I think. Good. Okay. Very nice. So if you found anything different in this example, go back, adjust the previous page, really flesh that one out. And again, if you have questions on it, let's take time to develop it. It's going to be a really good reference for you.